Hello, everyone, we are the ZhiyunShuiwuTeam. Next, I will introduce to you our ideas, methods and results in the battle of leakage detection and isolation methods. I will elaborate on it from the following 6 aspects: team introduction, competition analysis, demand calibration, pipe burst characteristics, burst detection and burst location. This is our team member, including Dr. Zhang Weipian, Professor Liu Jinqing, and 6 colleagues. Each of them divided their work according to their expertise. Here is the analysis for the competition. The data provided by the sponsor mainly include SCADA data, one water distribution network, and burst record data in 2018. The general idea for the competition is that, first, distributing node demand according to user pattern and demand in reservoir flows. Second, using WNTR tool and SCADA data to realize real-time hydraulic simulation. Third, calibrating node demand in order to make the simulation results and the monitoring results more closer. Fourth, by designing multiple indicators, we quantitatively describe the difference between the real value and the simulated value of the monitoring point, so as to identify the occurrence and end time of pipe burst. Finally, the burst location is contracted by comparing the fuzzy similarity of each pipe, which is designed according to the pipe burst characteristics. Next, I will present the demand calibration method. The main idea is to establish the mapping relationship between node demand and monitored value based on DFM, Deep Fuzzy Mapping, algorithm. DFM algorithm uses an infinite dimensional fuzzy membership function to represent the uncertainties regarding a functional relationship and is thus the fuzzy equivalent of Gaussian process. The main idea is of introducing a finite pairs of input-output points, referred to as the auxiliary inducing points, to be interpolated for defining a fuzzy membership function on functional output values. The designed fuzzy membership function-based data model can be applied for solving filtering, prediction, and classification problems. There are some important characteristics of pipe burst that we found through burst simulation, as shown in the figures on the right, mainly including pressure reduce, distance effect, and ranking change. These features play an important role in guiding us to identify and locate the pipe burst. When we carry out the burst detection, the first feature of burst detection is burst pressure differential summation value, which is calculated by the sum of the differences of each monitoring point. The difference value is calculated by the simulated value of the hydraulic simulation monitoring point and the real value, referred as system-per. The second feature of burst detection is abnormal node ranking, which is calculated by ranking the monitoring points in descending order of magnitude of difference. Then we obtain the burst time as follows. First is about the original evaluation of pipe burst time and confirmation of pipe burst times through the abrupt change of system error curve to evaluate, as shown in Fig 1. Second is about confirmation of pipe burst time. The pipe network status changed before and after the pipe burst. Select the top 10 moderated nodes during this period and calculate the number of the same nodes at different times. When the same number of nodes mutates, it is the time that the burst occurs or ends, as shown in Fig 2. The following tables shows the results of burst detection, where our model well verifies the burst time in 2018, see Table 1. Based on the data of 2019, we have analyzed the times and specific time of pipe burst, see Table 2. After we determined that the burst occurred, we began to find the location. The idea is based on the burst location characteristics of each pipe, and the method of fuzzy similarity priority is applied to select the most similar pipe segment with the real burst location characteristics as the burst pipe. The fuzzy similarity indexes include Pearson correlation coefficient, Jacquard similarity coefficient, and harming distance. The following figures is the location results, where the red line is the real burst pipe, and the green line is the model position pipe, from which we can see that our model can accurately locate the burst pipe. Based on the analysis of the data in 2019, we identified that there are 8 pipe explosion events in 2019, including 6 in Zone A, 1 in Zone B and 1 in Zone C using the model we proposed.